Hi, everyone, and welcome to the final project in this JH course for software development of real-time systems, real-time embedded systems. This is project number 10, as just mentioned. This is really the whole shebang. It's meant to be the kind of culmination of all of the previous projects all into one, where we have a quadcopter with IMU data captured in Arduino, sent to an RPI over an I2C interface, as well as GPS and video, all captured on that RPI as well, of course, and downloaded via Wi-Fi from the RPI to a host PC. So that's a mouthful. But again, this is just really mostly a culmination of everything from projects 6, 7, 8, and 9 in different ways. And the only real addition is this notion of an I2C interface to the RPI, although I'll describe kind of the software we use in order to facilitate that. So really the concept of operations here is that we are gathering all the capabilities that we have garnered, after project 4 from project 6 to 9. The goal of the project is to once again gather the IMU data, GPS data, and video on a flying quadcopter, and then from there use the RPI to collect all of it and stream it to a host PC using Wi-Fi. So some really basic stipulated requirements. There needs to be an Arduino, a webcam, an RPI, and a Raspberry Pi and a GPS module all on the quadcopter. The Arduino is going to be the primary microcontroller grabbing data off of this BNO055 IMU. It's going to capture yaw, pitch, and roll data and transmit that data to the RPI, the Raspberry Pi, over an I2C interface. The Raspberry Pi is also going to have the ability or need the ability to capture live video and capture GPS data. And all of that needs to get streamed via Wi-Fi to a host PC. So some derived requirements, as mentioned, this has now become a pretty complex system. It has several components associated with it that all get mounted. It is an application embedded software, an Arduino microcontroller that's running that application embedded software. There is an inertial measurement unit, GPS module, webcam, host PC, Raspberry Pi, a Python software to run on that Raspberry Pi, and finally a quadcopter. So that is all the components that really constitute this system. Of course, there's other things like, a battery pack, a flight controller, all that stuff, but really nothing that we're notionally in charge of for these projects. So to describe that application embedded software in a little bit more detail, it's going to be running on an Arduino Uno, and it's going to be written in C or C++. The application is going to periodically collect and transmit IMU data at a pretty high frequency of 10 hertz. It's going to get you yaw, pitch, and roll data, as well as calibration status of the IMU system as a whole, the gyroscope, accelerometer, and magnetometer, which are 3 components that constitute that IMU. I also have Python software that is going to periodically read the IMU data over an I2C interface. I decided to keep this at a much lower frequency. It's only gathering that data from the I2C interface at a frequency of 1 hertz, and then displaying that on the terminal on the Raspberry Pi. A few other things that I'm using here. One is a wireless access point, which I'm using a RASP app from Project 6, I believe, was maybe the first time we used RASP app. It's really a free software, free to use software that can run on the Raspberry Pi OS pretty easily. And that enables one to have a wireless access point running on the Raspberry Pi, and it's useful for transmitting GPS data, the video data, and IMU data over a VNC connection. So it's quite nice, especially because I'm flying this quadcopter outdoors with no reasonable access to a wireless router. So being able to connect my host PC to the Raspberry Pi via a wireless access point is tremendously useful. We're using the Motion software to facilitate live streaming of the webcam. Again, Motion is a free-to-use software application that works on RPI platforms, and there's some documentation on what that Motion software is. And then finally, we're using this GPSD software to facilitate GPS data collection of the GPS module that we have mounted on the quadcopter. So that's a mouthful. That is really all the stipulated and derived requirements necessary to for this project and what we're going to strive to accomplish. And so let's get into the design. The hardware setup for this project is really, really similar to a lot of the prior projects in this course. Really, the difference between Project 8 and Project 10 is just the addition of a GPS module. I believe the GPS module was Project 7. Since Project 7, I haven't really been using the GPS module much. It's been connected and in part of the systems, but I just haven't been streaming the GPS data. But now we're incorporating it back into the system. So again, because this is the culmination of all the previous projects, we are using a ton of off-the-shelf software for this project. We are using the Raspberry Pi OS. I'm using the 64-bit version because I'm running a Raspberry Pi 4. So I just grabbed the latest kernel and Debian version that is stable release. I'm using the Motion software. The most up-to-date version, I believe, is 4.5.1. I'm using the most recent release of RaspApp, which I believe is 2.8.8, as at the time of this recording, at least. I'm using GPSD. Again, a pretty recent release, 3.2.5, and then PuTTY, again, a relatively recent release in 0.74. So I've mentioned this before in the requirements, so I'll just skim over this part. But RaspApp, again, key for a wireless access point so that I can connect my host PC to the Raspberry Pi over Wi-Fi without a wireless router. Motion for camera recording and live streaming of the webcam. PuTTY, I'm using that just as a serial monitoring application so I can talk to the Arduino and confirm that it is getting all the IMU data off the BNO055 IMU sensor. And then finally, I'm using GPSD, but more specifically the CGPS client that gives me latitude, longitude, and altitude information in a nice handy terminal window like the one shown here. And so speaking to a couple software packages that are more custom for this project. One is the Arduino embedded software, which I described in the requirement section above. Unlike previous projects like Project 8, I dropped the use of free RTOS because it's not a requirement for this particular project. And instead, the key requirement here is to have the Arduino communicate with I2C devices like the IMU, but also act as a slave for the Raspberry Pi, so that the Raspberry Pi can communicate to the Arduino over its 40-pin GPIO header, specifically the SDA and SCL pins of that GPIO header to facilitate the I2C interface. The software design is pretty simple. There's really, two pieces of software running in parallel with one another. One is that Arduino application embedded software that I just mentioned, which talks to and gets orientation data from the IMU. And then there is a Python code that's running on the Raspberry Pi itself. And the Python code is enabling the ability for the Raspberry Pi to request readings from the Arduino over I2C. From those I2C packets, it is extracting the roll, pitch, and yaw data. Then it is printing that roll, pitch, and yaw data over the terminal. So you can see that just right on the Raspberry Pi screen. And so that's all well and good. That is really, the key to this whole project here, or the main function addition to this project, which is to have the Raspberry Pi communicate with the Arduino over I2C. And so I'll describe the Python and Arduino software in a little bit more detail, but it's really important to note here that I'm using slightly modified versions of Addison Sears Collins's software, which is described in Canvas. Sorry, it's just taking a little while for me to switch context here. This is this particular file, how to send roll, pitch, and yaw data over I2C from Arduino to Raspberry Pi.pdf. In Canvas, it is super handy. I use this as a really key reference through the course of this particular Project 10. Addison has provided his code for talking to the Arduino, or for the Arduino to talk to the IMU, and to talk to the Raspberry Pi over I2C. It's really a slightly modified version of an example example code from the Adafruit BNO055 library, but he has added the ability to have the Arduino be a slave to the Raspberry Pi for its I2C communication. And so this is immensely valuable. And in addition to that Arduino software, Addison has also provided Python code to run on the Raspberry Pi. I was very thankful for that. Python is not a coding language I'm super familiar with. So I have leveraged that considerably and really just made slight modifications, which I'll describe in the implementation section of this report. And so that is really the design of this system. We're using a lot of off-the-shelf software. Where it's not off-the-shelf software is slightly modified versions of code that is provided by Addison Sears Collins and is accessible on the Canvas website. So this was a really valuable document that I referenced quite a bit for this project. And let's move into the implementation here. So the implementation for setting up the RPI, thankfully, because this is the last project in the course, my Raspberry Pi has been set up with Motion, RASFAP, GPSD, and PuTTY from all the prior projects. And so I'll describe some of the terminal commands in just a moment here, but it's all part of this report. And for streaming viewing, all the IMU video and GPS data, the host PC connects to the RPI's wireless access point, and everything is viewed through a VNC viewer. And so that's really all we need here in order to set up the RPI. And of course, upgrading the Quad Copter. The Quad Copter is mostly built from previous projects. The key changes I'm making are to get the Arduino connected to the Raspberry Pi's 40-pin GPIO header so that I can facilitate I2C communication. I'll show some pictures of that in just a moment. I have the RPI hooked up to a battery pack, which powers it via USB-C cable. And then I'm connecting the host PC to the RPI via a wireless access point. Through that wireless access point and VNC viewer, I can start the Motion software, start up the CGPS client, start up a serial connection to the Arduino, run the Python code in a terminal to get the IMU data over I2C, and facilitate all of the requirements for this project. And all the commands for doing all of these above steps are detailed later on in this section. So some pictures of what the quadcopter looks like. I've seen a lot of changes over the past 5-6 weeks here. We have the Arduino, the BNO055 IMU. We have the web camera and the Raspberry Pi 4 with the case. And sorry, this is actually a slightly old image. I should delete this one. This is the most up-to-date image here. I apologize. This has the Arduino hooked up at the bottom of the quadcopter. The Raspberry Pi 4 is sitting here. I actually had to remove the top case of the Raspberry Pi, so it's actually fully exposed. But I needed to do that in order to get these I2C 2-wire connections over to the Arduino, so I can facilitate the I2C interface. So I apologize, this image is out of date, but these two here are up to date. This is the quadcopter with all of the new additions. It has the GPS module here. It has the Arduino at the bottom of the unit, the RPI at the bottom of the unit, the battery pack also at the bottom of the unit, the web camera, and everything we need for facilitating this project. And so this is the underside of the quadcopter. It's gotten a bit untenable, just the number of wires and components that we have on this quadcopter. I'm very glad it can still fly, but of course, it is getting a little bit messy. And so cable management is something I've been struggling with for this project. Let's talk about the Arduino software just a bit here. Once again, I have to thank Addison Sears Collins and his document, which is captured on Canvas. I have leveraged his Arduino code mostly out of the box. I had to make a couple small modifications, which you'll see here in this report. I updated the serial communication baud rate from 9600 to 115-200 just because that is what I've been using for all my previous projects. So I wanted to make sure the baud rate stayed the same because a lot of my configurations leverage this baud rate instead of 9600. My PuTTY terminal on the Raspberry Pi is already set up to read at a baud rate of 115-200. So making sure that works. I'm also using Visual Studio Code and Platform I/O, and so the way that you need to write Arduino software in Visual Studio Code and have it compile correctly, you need to have all of your functions cast at the beginning of the code, or they need to be defined before they're called in any other program. So I had to reorganize a couple of the functions in Addison's code in order for it to compile correctly in Visual Studio Code. But other than that, everything works right out of the box. It is fantastic. And I just flashed this onto my Arduino Uno, and it just works, which is terrific. So this is the code to run on the Arduino Uno. And then I also have Python code, which again is a slightly modified version of the script written by Addison Sears Collins. Again, this is where you can find it on the Canvas website. The only modification I made is in his Python code, he's requesting IMU data every 5 seconds. I'm requesting it every second because it's just nice to get that kind of more real-time feedback. And so that was really valuable to me. But other than that, it works right out of the box. As long as you save this Python script to the top level directory of the RPI, you under this particular file name, this ardu underscore pi underscore I squared C underscore IMU.py, you can run it straight from the terminal via Python command. So you just do sudo Python and that runs a Python script, and specifically the Python script that we have saved to the top level directory. And so this is the code. It's pretty straightforward. I'm not a Python coder, but even I was able to, understand this and update the sleep time so that that affects the IMU reading frequency. It is reading over that I2C interface once per second from the Arduino. And this function here, request reading, is the key function that facilitates all of this. It grabs a block of bytes from the Arduino via this I2C interface, and then it extracts the roll, pitch, and yaw data from that block of bytes that is sent over the I2C interface. And then it just prints it out, which is terrific. So you just get that in the terminal that you run the Python script in Raspberry Pi. And here are all the terminal commands necessary for getting the appropriate packages onto the Raspberry Pi. Once again, because this is the last project in the series, a lot of this software was already installed on my machine, but these are still the commands you would run in order to get CrassBAP installed, GPSD installed, Motion, PuTTY, and of course a couple other programs that were useful for this particular project because we're running a Python script in order to grab I2C data on the RPI. And then finally, in order to do all of the tasks necessary to complete the requirements for this project, you can start the Motion software with a couple quick commands, sudo service motion restart and sudo motion, that kicks off the Motion server, which then you can see on any old browser that you can run on the Raspberry Pi. So I'm just using Firefox. And so I can get a live stream on the Raspberry Pi of the webcam video footage. You can start the GPS software. Again, I'm using the CGPS client because it's nice and clean, gives me longitude, latitude, and altitude, all displayed in the terminal. And then finally, I am using PuTTY to create a serial connection to the Arduino. Once again, that's only for checking the serial data stream that I'm getting from the IMU, so I can make sure that I'm getting the requisite roll, pitch, and yaw measurements. And then I can run the Python script, this ardu pi I2C IMU.py script, in order to get all of the roll, pitch, and yaw data from the I2C interface displayed on the terminal window running that Python code. And so all that said, I will now cut here. That is the full description of everything you need to get all of these requirements complete, of which there are quite a lot. And so I'll go ahead and cut here. The first thing I'll cut to is a pre-flight demo of me running everything on my host PC connected to the Raspberry Pi in order to show that I can get everything working without flight, just because that's, of course, a lot easier, and I can more easily talk about the commands that I'm using here to get things up and running. And then I'll cut into a couple live flight demos, hoping that everything goes well out in the field where I am connecting my host PC to the Raspberry Pi via a wireless access. So I'll cut here and I will show you what I have for you in terms of demos right now. Thanks much. Hi there, everyone, and welcome back. So we have a bit of a lengthy pre-flight demonstration we're going to do here, but it's all for the best. We're going to get our GPS module up and running. We're going to get our webcam up and running, and then we're going to get our IMU data up and running. So all three of those elements will be pulled up on the Raspberry Pi, which you should see here on the screen. I'm sharing my kind of VNC viewer. And so the first thing I'll do, I'll probably mostly start from scratch here. I just, before the video started, did this ls dev tty check to see that my components are connected to the Raspberry Pi. ACM0 should be the GPS module, and ACM1 should be our Arduino that is hooked up so that I can communicate over PuTTY. So the first thing I'll do is maybe just start off arbitrarily with the webcam here. So once again, I'm using the Motion software. And to get that started, all I do is open up a new terminal. I'm going to go and type in these commands, sudo service motion restart and sudo motion. And so what that'll allow me to do is then go to a browser and go to this particular address, and my webcam should come up. And let's hope that works as intended. One other note that I found is using Firefox is way better for the Raspberry Pi than using Chromium. It took me a very long time to figure that out. More than I care to admit, I suppose. And here we go. We have the webcam. I'll just put this off to one corner of the screen there so you always see that webcam in the background, and then we'll move over to the GPS. But just to show you that it is working at a slightly long lag. There you can see my little Lego flower assembly. And so the webcam module is working as intended. Now we're going to start up the GPS module. So let's go ahead and do that. And so in this same terminal that I used to start the motion, I'm going to run the cgps-s command. Oh, sorry, that's, I think there's supposed to be a space there. Here we go. And so unfortunately, what you'll mostly find is that because I'm indoors, I'm in a skyrise apartment. So, there's dozens of floors above me and dozens of floors below me and lots of walls. So you will not see any longitude, latitude, or altitude numbers here because the GPS module physically just can't see enough satellites, but that's fine. Once we get to the actual flight demo, I will go outside, connect to the Raspberry Pi over RASPAP, the wireless access point, and that'll allow me to actually see all the GPS data well and good. And so the final piece of all of this is to go ahead and start up my IMU data retrieval, and I'll go ahead and do that here once my VNC can reconnect. So we'll wait for that for just a moment here. Apologies for the delays. The Wi-Fi on my Raspberry Pi has been a little bit spotty. I think somewhat stemming to the fact that it's been damaged from all the flights I've been doing. And we're back. Okay. So I'm going to go ahead and minimize this window. The first thing I'm going to do is actually show you that the Raspberry Pi is connected to the Arduino over USB serial. And so I'm going to be able to open up a PuTTY window here. Maybe any day now. There you go. So I'm going to load this. And because I have a GPS module attached, my Arduino Uno will get pushed down to ACM1. So I'm going to go ahead and open that. And there you go. I get the telltale signs that everything is alive. Now my gyroscope is calibrated. And the nice thing about the webcam is you'll see me be able to calibrate the magnetometer now. So I'm just throwing the quadcopter around back and forth. My webcam seems to have crashed on me. Apologies for that, but there you go. Oh, now my magnetometer has uncalibrated itself. Wow, that magnetometer really doesn't want to calibrate. Okay, I'm going to leave it at that. And go ahead and run my Python code, which is giving me the roll, pitch, and yaw data just the same. And so these should match 1-to-1, assuming that nothing kind of breaks. So I'm just moving my quadcopter around. The magnetometer does not seem to want to calibrate for whatever reason. But if I pitch upwards, I see the pitch change. If I pitch downwards, I see the pitch change. If I yaw clockwise, I see the yaw change. If I yaw counterclockwise, I see the yaw change. And if I roll, I see the roll change. And if I roll counterclockwise, I see the roll change again. And then I get to go ahead and put down the quadcopter on my desk, and the pitch values stay relatively low. So here we are. The device is kind of calibrated. The GPS module is collecting, and I'm going to go ahead here and try to reload my web camera. It seems like, oh, there you go. Sorry, it's just with all the spotty Wi-Fi, the GPS module crashed. So let's go ahead and show you again. I'm going to go ahead and pitch upwards to the ceiling, and my pitch value is changing here. I'm going to pitch downwards towards my desk, and you'll see the pitch change there again. I'm going to yaw clockwise, and you'll see a nice VNC viewer. I'm going to yaw to the other side, and you'll see my lamp. I'm going to roll. Here we go. So that is a roll counterclockwise, and then a roll clockwise. And there you go. And everything's kind of shifting on my quadcopter because I have so many components attached. But I'm going to set this down once more, and you'll see the pitch value go back to 0. And the webcam kind of settles out here. So this is the live demonstration that you're seeing here for roll, pitch, and yaw, and the web camera screen. So that is pretty much where we're going to get to with this pre-flight demo. I'm going to go ahead and close everything out and restart everything for the actual live demo. So I'll cut here, and we'll see you again soon.